Hello and welcome to the video directions accompanying Lab 2. The purpose of this video is to help you with the more technical side of analysis in the lab. If you want to see the overall background of the lab on the topic of conservation of energy, look at the handout. Also, the handout will tell you what you need to turn in. All right, so in this particular lab, we're looking at the energy of a dropping ball. And so I have recorded a video of my daughter dropping a ball. I used the slow-mo setting on a iPhone, and then I've just imported that as a .mov file, which works fine in VLC, the software that we've used before. All right, so here I've gone and opened the video in VLC, and I'm going to use a new shortcut key to switch through the video one frame at a time. And this is a very simple command. You just push the letter E on your keyboard. So you can see E advances one frame at a time. Now I'm going to drag the quick bar here to move up to the point where I want to be. All right, because I wanted the drop to maybe get the interesting part of the drop, so I'll start there. Okay. Now one thing I'm going to be looking at is this stopwatch. Okay, this is a stopwatch program that I found off the internet. I'm not sure if there are better ones. This is the one I'm currently using, and I would recommend you use it as well. I mentioned it in the lab handout. It has fractions of a second shown here, but it doesn't count through every single one of them. So it's going to be counting, but it's not counting on the actual, because you can see this would be a 1/10 of a second, the 9 place, the 5 place would be a 100th of a second, and the 3 place would be a 1,000th of a second, which would be great if it was actually counting every single one of those. It's not, and again, I'll be on the lookout and make an announcement if I find a better program online, okay? So let's go ahead then and take this one. We can see here that this would be 953. We're going to look till when the clock advances. So I want to save an image. One thing I want to check is where that image is being saved. We've done this before. I'm just running through this step. We go to Preferences on the VLC and go to Video. This is where video snapshots are taken. This is how we're going to create our image stack for the purpose of analysis in ImageJ. All right. And so I've created a folder called Temp. Make sure that folder actually exists within my download folder. It does. So I'm in good shape. Okay. Now, if you don't want to import to ImageJ at all, you could put your data directly into Excel. And I'll talk about the data I'm putting in Excel. And that would work if your measuring tape, if you're able to see all of the values exactly in your measuring tape. Due to the distance I was filming at, you can see that the values in the measuring tape are too blurry, and so I can't see them. And so that means that I'm going to instead use analysis in ImageJ based on pixels. And pixel equivalents to find out how long that meter stick is. Okay, and I'm going to show you that step because some of you might also have blurry measurements in the background, or maybe you just have one fixed measurement. Maybe you tape something to the wall that you know is a few 3 centimeters long. Well, as long as you then tell ImageJ the exact length of that object, and as long as that length is basically at the same depth away from the camera as the ball, then you're going to get all your distances just right. And again, your times are going to come from your stopwatch in frame. All right, so let's then go ahead and take this as our first image. I'm going to do Option Command S on a Mac. It would be Option Alt S on a PC, and that's going to save one image to the directory that I've told it to, like I showed you before in Preferences. All right, saved. Okay, now I'm going to advance one frame at a time. I'm not going to save every frame, but instead I'm keeping an eye out for when that 953 and the fraction of the second advances. Okay, so now we're at 988. That's a great opportunity to take another frame. So Option Command S. Okay, I'll advance a few more frames so we get a clear advancement in time. Okay, 022. Let's wait till it stops being blurry. There we are. Okay, and it's probably kind of good to find one sort of in the middle of 022, right about there, because you can see that again the clock is not. It's taking fractions of a second, but not every single one of them. So here's another image to save. Okay. I don't know what I did there. All right. So advance some more frames. Our time jumped again. Good. We're in good shape. Again, get to it when it's not blurry. Good. All right. Option Command S. All right. Advance some more frames. Okay, Option Command S, advance a few more. All right, there we got a 155, looking good. Option Command S. I bet we can get one more before it hits the ground. I'm just going to show you kind of part one of the procedure, which is the free fall part. Looks like it froze up a bit. So mine just froze up. It's actually not a problem. So this is worst case, it freezes up. You don't lose everything. You would just quit VLC, reopen that file with VLC. Here's the drop, by the way. Kind of fun to watch in slow-mo. There it goes. Okay, and then that would be this would be the bounce that you analyze from that first bang to the second bang. All right. So what we'll do then is we'll go to the folder where I have been saving my images and find the last one. Okay, I open that up. That reminds me that my last one was at 155, 42155, but I really only care about the 2155. All right, and so then I can get back to that stage in the drop pretty easily. All right, and I kind of remember where it was as well. All right, so the 55 was. Let's see. So of course we're going backwards. Okay, so we get down there, and we've got our. See, it started to freeze up on me again. I don't know. Been going back and forth too much for its liking, but again, you can always just restart it. Okay, so now going back, that's it hitting the ground, and now here's the drop. So 155 was before it hit the ground. We get we get a 188 right at the ground. All right, so that would be that point right there, 188. Okay, so this will be the last image I save. So I'm going to do Option Command S. And I know I didn't go frame by frame there. I was just trying to find it in a hurry. So let's go back to our folder and look at the images that I've saved. All right, so I've got that last one. Okay, and as far as this last one ends up with a different name. Let's see, because I had to restart the program, so you can see it has like a unique name to it. Let's go ahead and just label it. So I'm just going to take the name here because I want ImageJ to get the names right. So I'm just going to copy the name of the last one that was in order, give the one that should come next, and just give it a number bigger than the following numbers of 47. Change that to 48 instead. Okay. So now I've reordered my images correctly, and you can name them any way as long as the order is correct. So I ended up with 1, 2, 3, 4, 5, 6, 7. Now I asked for a minimum of 10. That means at this rate, using this software and the limitations of how many fractions of a second it shows us, you would have to drop it a little bit higher than my daughter dropped it. Okay, so another couple feet, and you should be able to definitely get all 10. Okay, that's just it shouldn't be a problem to get all 10 images. I'm just kind of showing you the process. Okay. All right, so from there, now we're in good shape. We got a good set of data that we can go ahead and import into ImageJ and analyze. So here I have ImageJ opened up. Mine is just called Fiji, but of course that just stands for Fiji is just ImageJ. They're identical programs at the basic level. All right, so let's do File, Import, Image Sequence. Got my temp folder. I'll go ahead and import it. Here are my 7 images. Save, just keep the default settings here. All right, and let's bring them all in. Okay, so now we've created something that we can analyze. Now, the first thing we want to do, first thing we want to do is to set our scale for ImageJ. And again, you don't have to do any of this if you have a perfectly clear, non-blurry measuring tape, because then you could just take the readings off the video itself and not have to do any analysis in ImageJ. But I want to show you this because you can't get it to not be blurry, and I don't want that to be a dead end, so I want you to show you how you can do it. Okay, so what you do then is you would go to Analyze, and then you're going to Set Measurements. Okay. All right. Excuse me, that's the wrong thing. You want Set Scale. Excuse me, not Set Measurements. Set Scale. All right. So I'm going to have a known scale. I'm going to tell it how far that known scale matches up to a particular distance, and then I'm going to make that global so it applies to all images in my stack, so all 7 of them. Okay, so to do that, I take the line tool. I'm then going to do Command Z to zoom in on my measuring tape. Now, ImageJ has a very clever but new way of probably new to you way of zooming. It will zoom to whatever point your cursor is at. So I left my cursor over here. It's going to zoom to the corner of the image, but I want to zoom on top of the measuring tape. So while the cursor is over the measuring tape, I'm going to do Command Z. Excuse me, Command plus. I don't know why I thought Z. I thought Z for zoom. So excuse me there, Command plus. Again, Command plus. And this would be Alt plus on a PC. Okay, so now I've got zoomed in. Obviously, again, too blurry to read. But what I'm going to do is I'm going to draw a line from a centimeter mark to a centimeter mark. Okay, so that would be from here to here. And I've confirmed by looking at the measuring tape in front of me that that is the centimeter mark. So you can do that with whatever thing that you measured. I don't know if I mentioned this already, but you could also just tape up something of known length. Like you can look up the exact, if you don't have any measuring tape in your house, you can look up the exact dimensions of your cell phone, right? Because those are technical specifications, and then just measure that, kind of mark it off on a piece of paper with a pin, and then tape that piece of paper to the side of the wall that you're dropping an object in front of, and then that's your known distance that you would set your scale with an image J. So you don't need a measuring tape at all. Okay? Now I'm going to go back to Analyze, Set Scale. So that distance in pixels is 26.0768 pixels long. Remarkable, right? And I know that is exactly 1 centimeter long. Okay? The unit is the centimeter. And again, I'm going to make that global, so it applies to all 7 images. There we go. We've set our scale. Okay? Now let's start pulling data off of our drop here. Okay? So we're going to have 7 times. Okay? So the first one I'm just going to call 0.953 because I don't care about the previous seconds before the point in the drop that I started analyzing. Okay? So I'm going to have 0.953 as my first timestamp. Okay? Then let's advance to the next frame. Okay, I'll make this smaller so we can just do it like this. Okay? And then advance to the next one over here. Let me click away. There we go. I had to click away from the line tool that I used to set the scale in order to be able to advance with the arrow keys on my keyboard. So it's a good tip. All right, so now it's 0.988. Right, and remember I just confirmed that when I was looking at the images in VLC to find the next one that showed a distinct time on the web-based stopwatch. And we're going to advance again 1 frame. This one now would be, because we've progressed 1 second, so I would call this 1.22. Okay, now we're going to advance again, and this would be then that would be 0.22. That's very important. And this one would be 1.087. Okay. Okay. And then now 1.120. Okay. You see Excel just drops the trailing 0, so it doesn't matter. Okay. And then 1.155. All right. And then 1.188. Okay. So now all I need is the distances that correspond to those times. That's where image J comes in. And again, if you could just read them off the measuring tape, you're done. You would literally just go, you wouldn't even need image J, you would just look at your images or even VLC itself and be like, oh, well, the ball is right, because the measuring tape maybe might be off to the side. Maybe you did the drop, so the measuring tape is just immediate to the side. And you look at the center of the ball or some fixed point on the ball that you've been using for each measurement. You look over on the side-by-side measuring tape and you say, oh, well, that's at the 27.2 centimeter mark, okay? And then, whatever fraction of a second later, it's at the, if it's going down to the end of the measuring tape, maybe now it's at the, 22.8 centimeter mark, right? So you could just do that, okay? But I'm not, okay? So what I'm going to do, go back to the first frame. I'm going to use the point tool. I'm going to set up options to save me trouble. Auto measure, auto next lights. I don't really care about adding it to the overlay or anything like that. Okay. All right. Looks good. All right. And then I'm going to click on the center of the ball. And then I'm going to click on the center of the ball. And then I'm going to click on the center of the ball. The center of the ball. The center of the ball. Center of the ball. Center of the ball. Okay. So now let's see how it looks. Okay. So here's my data. And what I'm interested in here is the position that is my X position, because my image is tilted. And so these are just the distances that the ball has traveled in X direction. It doesn't matter that it's 23, it could be 3. What matters is the difference between each of these subsequent X measurements, okay? Because the X here corresponds to the vertical displacement of the ball, because that's what we're going to use to calculate the potential energy of the ball, its potential energy to fall. And then we're going to relate that, of course, to the kinetic energy of how much speed it's picking up. All right, so I'm just going to copy this data in, okay? And let's see, I think Might be able to just do a cut and paste. Let's try. Yep. All right. And so I just did Control C and then Control V. And the only data I care about is the data from the X column. So I'm going to cut that data with Control X and then put it with Control V into the vertical displacement. And then I'm going to clear the rest of this data off of my Excel workbook. Right click and then do Clear Contents. All right, so there we go. All right, so I should point out that this time is in seconds. It's good to have the units right here in Excel to remind yourself what they are. And vertical displacement is in centimeters. Okay, so now we're going to create a new column. Make some space for it so we can see the full name of the previous one. We're going to call this one velocity. Okay, so in the velocity column, we're going to use a calculation. I'm going to do an equal sign to tell Excel that I want to calculate one cell relative to another. Then I'm going to take the difference in displacement. So I'm going to do the cell that is in the vertical displacement column, but one row down from the velocity cell that I'm working on. So yeah, click on that. Okay, and then I'm going to subtract, just pushing the hyphen, the vertical distance that is in the same row as the velocity I'm calculating. Okay, because what that represents, and I'll put parentheses around it, it represents delta y. And I described that in the handout. That's the change in vertical displacement. And I'm going to divide that by delta t, because change in distance, in this case vertical distance, divided by change in time is the definition of speed and also velocity. Okay? And then I'll do the same thing with time. Click on the cell that has the next time step minus the cell with the current time. There we go. So that represents the velocity, the average velocity between 0.953 seconds and 0.9988 seconds. In other words, the average velocity when the ball was falling from a height of 23.239 to 26.537. And this, of course, these numbers are getting bigger because the height is measured relative to the ceiling. So you can think of it as a depth from the ceiling. Okay? And what I can do now, Excel is very smart, you can grab the lower right-hand corner of this calculation, and it will do the same exact calculation for cells that have the same proximity relative to the velocity cell. So check out what happens. I drag it down, and I get the average velocities between each of these displacements, or in other words, between each of these times. Notice that I don't fill the last one, because if I was to ask Excel to calculate the velocity here, it would be looking at these empty cells in the 9th row. Since there's nothing there, it would just give me an error. See? Okay. Gave me not an error, but it gave me a nonsense result because I wasn't dividing by 0, so there was no error, but it gave me a nonsense result. So we definitely don't want that. Okay, I just deleted it. So here we have our average velocities. They should be speeding up. Okay. Let's see. We definitely have some oddities here, right? We're jumping around. I'm trying to think about why that is. Okay, so let's go back so I can quickly assess anything here. So we had one, we got the 2 seconds, traveled a certain distance. Okay. Because it should be speeding up. So at first it wasn't moving much. We definitely see there, and then it should start to speed up. Not all the time. The times are the same. So that's why I'm like, oh, okay, there's a much smaller difference here, but that should be less time. That was a smaller time difference if I look correctly. 1.155. Make sure I didn't make an error. Any of them? No, and they're kind of standard. They're actually moving. So it could definitely be a limitation with the stopwatch. Let's see. Trying to quickly troubleshoot this while still making this a useful video for you all. Let's see. So, okay, yeah, so we have a nice big chunk there. So those ones seem good. So why is this one so large? Why do I have... Because here I went from 988 to 0.22, which was 40 thousandths of a second later. And I went pretty far in that step. as you can see. The ball is falling basically, in the straight direction, and it's not like it wasn't like thrown outward. So I don't think I'm worrying about a third dimension of movement here. Just thinking about what potentially is going on. I think it's probably because when I was looking at VLC, I was trying to find the moment. At first, I was just trying to find the moment that the new time came, but I think I wanted to be more careful about finding the exact middle of that time. So let me go show you what I mean. So here we are back in VLC, and if I go back and we'll get to a point, and I actually should have started it sooner to get some more usable data. But then if I start advancing one frame at a time, and here we have if you look over at the time 920, it stays 920 for quite a few frames. And I think I made the mistake on one of them of taking the first frame when it changed. Like here you can see it changed to 953, but I want to find the middle frame of it being 953 because it stays 953 for quite a few frames, right before it's 988. So that was my mistake. You need to find the middle frame where it is that time. Okay? Does that make sense to everybody? Okay? I know you can't answer, but that's an important thing that I want you to understand. Is that, so let me show you an exact example. Okay, so let's see if we can get it to actually start playing again. No. All right, let's reload it. Okay. Okay, just now open it up with VLC again. Okay. Okay, so let's do E, 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 E. Okay. Nice moment of the drop here. The flashing light, because we're filming faster than the frame rate of electricity, which is 60 times per second. Okay, so here's a good example. So 787, okay? So where's the end of 787? Okay. Ugh, it's really annoying how much it freezes up. Okay, so let's see. Okay, so there. So we have 787, right? So we'd have first frame of 787, second frame of 787, okay? So let's see if I can kind of actually show that. So E. Okay, so right there, it's now, you can see it's just blurry changing to 787. Okay, now so that's 2 frames of 787, 3 frames of 787, 4 frames, 5 frames, 6, 7. Okay, now it's gone. Now it's 821. Okay, so there are about 7 frames of a given time. Let's see if it's the same for 821. Okay. So 821, 1 frame, 2 frame, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? So that one was about 12 frames at 821. Because again, it doesn't take exactly even steps. So it makes sense that it's not going to be exactly the same. So 12 frames of 821 before it changes to 856. All right? So that means you'd want the 6th frame of 821. All right, so you need to find the 6th frame of 821, and that is the only way you would get an accurate result. Okay, so that is very important. Okay, and that's why my data isn't looking that accurate, because I just kind of took arbitrary steps of frames that all had the same timestamp. All right. So, how did I know that? Well, because first I had a velocity of 92, then I got bigger, then smaller again, then bigger, so it's just kind of jumping around, okay? It shouldn't be. It should be gradually increasing, okay? So let's go ahead and at least show you what it might be looking like. So we'll just go ahead and create some example velocity here, because I've shown you how, but I don't want to redo the step of analyzing the velocity. So we'll do an 80, 95, okay, and I'm kind of taking inspired by these numbers here, then 150, 260, and then we'll just do a new one, 310. Okay, so then I want to show you the last step in terms of analyzing in Excel to conclude this video. Okay, so what you do then is you want to create columns for potential energy, PE, and kinetic energy, and total energy. Okay, so you would calculate potential energy as the mass of the ball, which you'd have to weigh. So this ball weighed 100 grams. Okay, so now my unit's going to be in kilograms. I'm going to multiply, use the multiplication symbol, which is the shift 8. Okay, then I'm going to multiply by the height. Okay, well, first by gravity, so 9.8. Okay, because it's m times g, which is gravity, and then times the height. Okay, so it's the height off of the floor. So if you look here, the height off of the floor is the difference between the maximum height minus the current height. Okay, so then I would do parentheses, the final maximum height, because again, the floor is technically a larger x value than the release point. You could fix that, I suppose, by flipping upside down, and then minus the current height, because that, or current vertical position, because that will give me my actual height. And let me actually call this column vertical position, because then the difference between them represents height. Okay, so again, that's the formula I've used here. So then this is going to give me units of centijoules, because I'm using centimeters. So if I want to get units of joules, then I would divide. Actually, this would not give me cent. This would give me hundreds of joules. So I have to divide by 100 to get the appropriately small value, which is going to be joules. Okay, because again, that converts from centimeters to meters by dividing by 100. Okay. So then I'll put the units right here. The units are J for joules. Those are the units of energy. The same units are going to be on kinetic energy. So joules again. Okay, and then we would do our velocities. Again, these velocities are made up. I'm sure that's frustrating some of you, but that's, again, I've shown you kind of a troubleshooting example. I've shown you how you have to be on the lookout for data that doesn't make sense. Then I found out what the problem was, and that's because I wasn't being careful about taking frames in the middle of each timestamp. All right, and you can address that by finding the frame in the middle. Okay, so ask me if that doesn't make sense. You can address that by looking out for an announcement if I do find a better stopwatch program that is more accurate, because it'd be nice to have one that is really showing every at least 100th of a second, because this one is taking more like 1/3 of a second jumps. Okay, so that would be good. And then the third option is, again, just to have a non-blurry measuring tape. You would still want to find the timestamp that's in the middle, because the ball was still moving while the time was seemingly standing still, right? But then find the location in the middle, and then just record both the time and the vertical position, and not worry about image J, which at least would save you some trouble. Anyway, going on to the calculation for kinetic energy. There's a 1/2 in front, and all these formulas are in the lab handout. Then multiply by the mass again, in this case 100 grams, and you have to weigh your object or use an object of a known weight. Okay, and then multiply by the velocity squared. Okay, so I just click on this one, and then remember to square it. To square it, I use the what I call the caret symbol, which is shift 6, and then just a 2. Okay, so both these are formulas in Excel. They're calling on particular cells. See how this one's calling on these two vertical position ones. Potential energy is just calling on that single velocity. Okay, well, I can drag it down, and I can drag it down 6 rows. I'm going to use 6 rows because there's only 6 rows of velocity. So that's going to be from 11 down to 13, and then down to 16. Okay, and it should do the same calculation. So let's make sure it's doing it correctly. All right, so move down. Looks like it's not, so let's see about why. Okay. Oh, I see, because it's still, yeah, so I needed it to be fixed on subtracting, and I could have created another column where I just did that subtraction, but I needed to always subtract from 61.97. So to do that, I would lock that cell. So I'm just going to lock B8 by putting a $ in front of it. That way it will always subtract from 61.97, and the only thing that's going to be changing is the vertical position that it's subtracting from 61.97, because that's going to give me my height. Okay, so I take that new formula with the locked $ just in front of the 8. I could lock the B as well, but it doesn't matter, because Excel is going to assume that I'm only going to be doing calculations from column B, because it will only look at column B, because all my calculations for potential energy, although they're in column A, are in a single column. There we go. All right, so those are our potential energy measurements. All right, and these, you can see that the potential energy is decreasing. That makes sense, and that's because there's never an issue of our vertical position measurements. It was just our time measurements that were problematic. And so the potential energy decreasing at a gradual rate is indicative of the fact that the ball's falling. It's closer to the ground, thus it has less potential to fall. Potential energy is the ability of turning gravity into movement. Okay, so now let's do, this one will be easy on kinetic energy. I can just drag it straight down. Right? And then we see that our kinetic energy grows as well, right? So first is 320 joules, and then it grows larger and larger. Now there's a mistake here, however, because our velocities are in centimeters per second. So what I want to do then is I want to convert my centimeters per second into meters per second, and I have to do that within parentheses before I square it. So I divide my centimeters per second by 100, and then I square them, and they become meters per second. Okay? So, traveling 10 centimeters per second is the same as traveling a tenth of a meter per second, and if I'm squaring that value, well, I have to remember to do the conversion from centimeters per second to meters per second first before I square it. So the parentheses around C2 over 100 is making sure that the order of operations is correct as calculated by Excel. Okay, so now I have reasonable kinetic energy values. Then total energy is just going to be the sum of potential energy plus kinetic energy. That's it. Okay, all I've done is click on the cell that has the first potential energy, add the cell that has the first kinetic energy. Okay, that's my total energy of the system. Okay, and when I started recording, the ball was already in motion, so that's why we have that there. And then, if our values are correct, total energy should remain fairly flat. Okay, now we're going to graph all of them. I'm going to show you how they graph, and then we'll finally be done. All right, so I'm going to insert a graph. This is going to be a scatter plot. This is basically the only type of graph we use. Okay, and I want to graph potential energy as a function of time, kinetic energy as a function of time, and total energy. So I'm going to actually delete this graph for now, and I'm going to take all these values here, and what I'll do is I want to preserve all of my calculations. So what I'll do is I'm going to copy these values. I'm going to copy them down here to the next row. I'm going to do a paste special, and I'm just going to paste the values so that all those calculations they're not going to try to look for cells to do the calculations. So I preserved all the values. Then I'm going to take my time measurements, and I want the first 6 of them to correspond, and I'll put them there. Okay, that means I can go right into my scatter plot of potential energy versus time. When you select 2 rows like this, it will automatically create a graph. It will even label your axes, and it will have potential energy as a function of time. The second column, or the column to the right, will be the dependent variable. The column to the left will be the independent variable, which is exactly what we want. So I'm going to go to Insert, Scatter Plot. There we go. Okay. So now we have potential energy as a function of time. So notice the potential energy is on the vertical axis. I realize I can make this a little bit bigger for you. Okay, potential energy is on the vertical axis, and the time is on the horizontal axis, right? Because this is our independent variable, potential energy is our dependent variable. It automatically sets 0 over there. We probably don't want that. We want to set our minimum somewhere where we can more clearly see the data. We also are going to want to add labels to our axes. But right now I'm just going to show you how to add more data to this graph. So I'm going to right-click on the graph, and I'm going to go over to select the data. Okay, I'm going to select another set of data, series 2. All right, I'm going to call series 2 obviously kinetic energy. All right, and then for the x values, it's going to be the same time values. Notice how I'm just clicking on that little dialog box. I'm just clicking there, and there's dragging, selecting the cells that I care about. For my y values, clear that out, and I want my y values to be kinetic energy. See? Right? Now go back to that window. So there we go. I've created my kinetic energy. Let's see how it looks. All right, so there's my kinetic energy. It's going up, of course, because I kind of did some guesswork, and I started with data that was problematic because of the issues of timestamps. It kind of goes up a little at first, then jumps up, right? So it's kind of not what we'd expect. We should expect it going up more gradually, all right? Because essentially the potential energy is becoming the kinetic energy. Ideally, your total energy should remain fairly flat. Let's add one more set of data. All right, so just gonna click on my graph, right-click on it, go to select data. Add one more series. Okay, that last series is going to be total energy. So I just click on that cell. That's just giving me the name. And I could just manually type the name in. Our x values are going to be time again. All right. Y values are going to be total energy. Okay, we'll do OK. All right, and there's our total energy. So the total energy can have a dip in it. That's not unusual, but it should be fairly flat. So the idea is kind of there. I'm going to make it so we can actually see this a little bit. I'm going to change the format the axis, set the minimum at like 0.8. All right, that's on Okay, yeah, I could have set it at 0.9 for that matter. There we go. All right. And you shouldn't connect the dots. You should just leave them as data points like this. But the idea is that the orange potential energy, or excuse me, kinetic energy goes up as the potential energy goes down, the blue, and the total energy should remain relatively flat. You also want to do some steps here at the end, chart design. Your depths, this is where you're going to add so chart, let me make this a little bit bigger. Okay, so this is where you're going to add chart elements. So you can add your axis titles, so your label, the vertical and primary and horizontal and vertical axes. You're also importantly going to add the legend. All right, so here I can put a legend up at the top, which clearly tells me what the colors are in terms of potential energy, kinetic energy, and total energy. Right. And you can include a color version if you can in what you turn in. Otherwise, make this, if it is colors and it's just gray, and I can't tell, then I will mark that down. So in that case, you could change these to shapes in whatever way you want to. You can always look up how to do it, or you could just print it and do it manually for that matter. Okay, but that is the idea. Those are the steps. Okay, just be aware of the issues with time and a stopwatch. If you happen to have a stopwatch that it has large enough numbers, then use that. And certainly I was disappointed with the quality of the online one. I didn't realize it was as bad as it was. But again, I think I did a good job of showing you the steps. I certainly hope you feel the same way. And this video helps you complete the lab. I'm going to be available to answer any questions about it. All right, talk to you all soon.